Hi, welcome. In today's tutorial, we are going to model above ground biomass density using the GEDI level 4A dataset, Sentinel-2 data, spectral indices derived from Sentinel-2 data, elevation and slope data. We are going to run a Python code in Google Colab. We will use a random forest method to model above ground biomass density in the Mafungautsi Forest Reserve area in Zimbabwe. So let's get started. First, we start by importing the Earth Engine API and authenticating our access. So please make sure that you include your project ID so that you have access to Earth Engine. Right, next, we are going to import the necessary libraries such as GEMAP, matplotlib, NumPy, and sklearn matrix. These libraries will help us to handle geospatial data, visualize the results, and perform the necessary machine learning tasks. Following that, we need to import the project boundary. So in this case, we are going to use the World Database on Protected Areas, which contains up-to-date and a comprehensive source of information on protected areas. So here we are going to use the Earth Engine filters in order to filter to our study area of interest. So in this case, we are going to use Zimbabwe, and then we are going to filter to our study area boundary. So in this case, we are going to use the Mafungautsi Forest Reserve area, as I've mentioned. So we run this code to get the project boundary. Next, we will load surface. We will load the Sentinel-2 surface reflectance data and apply a cloud mask to remove the cloud-covered pixels. Note that here we are using Sentinel-2 data between January and April, which is the peak biomass growth period in the project site. So we are also going to display the Sentinel-2 data for the project area, and we also clip it to the project boundary. So here's the Sentinel-2 data for the project area. Okay, next we are going to compute the spectral indices that we are also going to use as additional predictor variables. So we are going to calculate the normalized difference vegetation index, NDVI, the soil adjusted vegetation index, SAVI, and the red edge spectral index, RES. So let's run the code to do that. We will also display these spectral indices. Okay, so here we have our NDVI, and then we have our SAVI, and then the RES. Okay, next we also want to include elevation and the slope as predictor variables. So we are going to derive elevation and slope from the SRTM dataset. And we're also going to display these predictor variables. Okay, so here we go. We have our slope and elevation dataset for the study area. Okay, next we are going to merge all the predictor variables. That is the Sentinel-2 bands. We have the spectral indices, NDVI, SAVI, RES, and elevation and slope. We are going to measure this collection and then clip it to the project boundary so that we have the same dimensions for the predictor variables. And here we are going to define the predictor variables as bands that we are going to include in the regression modeling. So we have band 2, band 3, band 4, which is the blue, green, and red. And then we have band 5, band 6, and band 7, which are the red edge bands in Sentinel-2. And then we have band 8, which is the near infrared. And then band 11 and 12, which is the shortwave infrared bands 1 and 2. As I've said, we have the spectral indices, the NDVI, SAVI-RES, as well as the elevation and slope. So let's run the code. Okay. And next, we want to load the GEDI level 4A dataset, which provides above ground biomass density data. So the above ground biomass data is our target variable in this model. So we are going to filter the GEDI data for this period between January and May, which is also the peak biomass growth period in the study area. Note that I've extended the period to May so that we have more GEDI data points for the study area. Right, we are also going to apply a quality mask so that we get quality GEDI data points. Right, we are also going to calculate the summary statistics such as the mean, median, the standard deviation, the minimum and maximum above ground biomass density in megagrams per hectare. Right, just for interest, also here, I've done the sampling at a scale of 30. So this is just fixed at one scale, that is the resolution, which is 30 meters. All right, let's run these lines of code. Right, we can see that here we have the minimum above ground biomass density of 48 megagrams per hectare, while the median is 49, and the standard deviation 29. The minimum here is 0.87, while the maximum is 228 megagrams per hectare. So there's high variability in the GEDI above ground biomass density for the study area. In total, we have about 4,632 GEDI points for the study area. So this is at the 30-meter scale or resolution that we have generated the points for. Right, we are also going now to display the GEDI points for project area of interest. Okay, so these are our points that we've generated in the project area. Right, next we want to prepare the training data frame that contains the target variable, which is the above ground biomass points derived from GEDI, and the predictor variables, which are the Sentinel-2 bands, the spectral indices, the slope and elevation. Note that here I've defined the scale or the resolution at which we are sampling to be 30 meters. So this is going to create a data frame that contains the training data set. So following that, we are going to split the training data set into training and test sets. In this case, we are going to use 70% for training, while 30% is going to be used for testing the model. We are also going to set the seed at 27 here so that we can get the same results when we run the model again. We are also going to print the size of the training and test data sets so that we know the quantities of the training and test data set. Okay. So if we run these lines of code, we are going to get our size of the training and test data set. So for the training, we have 3,249 points, while for the test data set, we have 1,383 points. Right. Next, we want to set up the random forest model that we are going to use to predict above ground biomass density. So here I've just set these parameters. We have the number of trees at 500, the mean leaf population at 1, and then the Beck fraction, which is 0.5. And then I've set the seed here to 27 so that we can reproduce the same results when we run the code. And I've set the output mode for the model as regression, since we are predicting above ground biomass density. Okay, let's run this code. And then next, we also want to check or understand the predictor variables that contribute most to the model. So we want to know which predictor variables is contributing most to predicting above ground biomass density. So in this case, we are going to use the RIF regressor explain function. So this is going to evaluate the predictor variables that contribute much to the model. So if we run this code, let me run again. We can also display the variable importance graph. Okay, so here we can see that elevation, band 5 and band 6, which are the red edge bands, are the most important variables that have influence in the model. But please take note that this variable importance is only showing the quantity or size of the contribution to the model, but it is not showing the direction of the contribution. By that I mean that it is not showing whether we have a positive or a negative contribution to the model. So this is something that we will need to look at in later tutorials. Okay, so after doing that, we also want to evaluate the model performance using metrics such as RMSE and R squared. So first, we are going to check the model performance using only the training data. So this is the training set. These are the points that the modelers have seen. Okay, so if we run this, we are going to obtain the RMSE and the R squared. Okay, on the training data. Right, it's going to take a bit of time. So here we are having the a very low RMSE, which is 12 megagrams per hectare. And our R squared is quite high, about 84%, 0.83. So this is quite high, but please take note, these results are very, very optimistic. So let's check the model, let's check the model performance on the test data set. That is the data that has not been seen by the model. So this is going to give us a more realistic evaluation of model performance. Okay, so you can also calculate the RMSE and R squared, and then plot the graph that shows the observed and predicted. Right, as we can see here, we have quite a high RMSE, which is 21 megagrams per hectare, and the R squared is very low, about 48%. So these results indicate that the model is overfitting. Okay, so this is quite a big problem. So the results are not that good. So we will deal with this problem in later videos. Right, but for the sake of this video, after we finish doing the model evaluation, we are going now to predict the model and then visualize the above ground biomass map. Okay. Okay, so this is our result. We are going to display the predicted above ground biomass density map. Okay, this is just taking a bit of time to generate the map. Okay, so this is our result showing the predicted above ground biomass density map in the project site. We can see that, let me just check this legend. The legend is not yet displayed, but it's coming. Okay, you can see that we have the highest above ground biomass density above 200 megagrams per hectare. So this is not, this is quite too high for the project area. 220 megagrams per hectare is quite high. So that means there's a problem with our model. We'll need to deal with this in later videos. All right, so after finishing your modeling or predicting the above ground biomass, you can export the map to Google Drive. So to do that, you just run this line of code so that your above ground biomass is available on Google Drive. You can download it there and then analyze the result in any GIS software such as a QGIS. Right, as we can see in this tutorial, we have a problem of overfitting because we can see that the model is doing better on training data, but is performing poorly on the test data. So we will need to fix this problem. Thank you very much for watching this video tutorial. The Python code for this tutorial is available in GitHub. while the detailed tutorial is available at IGO Labs. The download links are available in the notes below. Please don't forget to like, share and subscribe for more tutorials. See you in the next video.